Hey everyone. Today, we're going to unravel a force that, well, literally holds our world together. It's called tension. And yeah, it's in every cable, every string, every muscle fiber. But get this, it has some seriously counterintuitive twists that can fool even the smartest people out there. So, let's just dive right in with a classic physics puzzle. And trust me, this one is a real brain teaser. So, get ready. Okay, take a good look at these two scenarios. I want you to decide for yourself. Which rope feels a greater pull? Which one is under more tension? All right, so here's the setup. On the left, we've got scenario A. You see a 120 Newton weight just hanging from a rope that's attached to a solid wall. Simple enough. Now look to the right at scenario B. Here, that same 120 Newton weight is hanging from a rope, but this time the rope goes over a pulley and is tied to another identical 120 Newton weight. So here's the million-dollar question. Where is the tension greater, A or B? Go on, take a second, really think about it. Okay, so if you said scenario B has double the tension, you are in very good company. Seriously, that's the most common answer by far. I mean, it makes sense, right? The rope is supporting a weight on both ends, so double the pull? Well, as we're about to find out, the physics tells a very different and much cooler story. So before we can crack this thing wide open, we have to get our tools straight. We need to lay some groundwork and get a really solid working definition of what tension actually is. You know, at its core, tension is really just a pulling force. That's it. Think about a game of tug of war. That force you feel yanking on your hands, that's tension. And notice how it always pulls inward, right along the line of the rope. Okay, let's break down the golden rules of tension. First up, you can't push with a rope, right? It only pulls. Kind of obvious, but important. Second, and listen up, because this is the big one. The tension is the same everywhere along that rope. It's uniform. And third, it pulls with the exact same force at both ends. The pull on one side is perfectly, and I mean perfectly matched by the pull on the other. So why? Why is the force equal at both ends? Well, it all comes back to one of the titans of physics, Isaac Newton. You've heard of him. His famous third law tells us that for every action, there's an equal and opposite reaction. Forces always come in pairs. The rope pulls on you, and you pull on the rope with the exact same force. And here's a perfect way to picture it. Imagine you hook two of those springy force sensors together with a string and just pull them apart. What do you think they read? They don't show different numbers. Nope. They show the exact same reading. That, right there, is Newton's third law in plain sight. And it's absolutely the key to understanding tension. All right, so now we've got the tools. We understand Newton's third law. We get how tension works. Let's go back and solve that puzzle once and for all. It's time for the big reveal. Okay, here it is. This is the crucial insight. That second weight in scenario B, it's just doing the exact same job as the wall in scenario A. Think about it. The wall pulls back on the rope with 120 newtons of force to keep it in place. And that second hanging weight, it does the exact same thing. It's just a substitute for the wall. See, in both scenarios, that first weight is just hanging there. It's not moving up, it's not moving down. It's at rest, or what physicists call equilibrium. And what that means is that all the forces on it have to cancel each other out completely. So the downward pull of gravity, which is 120 newtons, has to be perfectly balanced by the upward pull from the rope. And there it is, the big reveal. The tension in both ropes is exactly the same, 120 newtons. That second weight doesn't add to the tension, it just provides the necessary reaction force to create the tension in the first place, just like the wall did. Mind-blowing, right? Fantastic. So we've totally nailed tension in a static system, a system that's not moving. But what happens when things start to accelerate? Let's switch gears and look at a dynamic problem. Okay, for our next challenge, picture this. We've got 3 sleds, all with different masses. They're tied together with ropes, and someone's pulling the whole train across the ice with a force of 120 newtons. Now, obviously, those ropes connecting them are going to be under tension. But how much? And do you think the tension is the same in both ropes? Now, to figure this out, we can't just guess. We need a solid strategy, a game plan. So here's what we're going to do. First, we're going to zoom out and treat all 3 sleds as one single massive object. From there, we'll figure out the acceleration of the whole system. Then, once we have that magic number, we can zoom back in and look at each part of the system to find those hidden tension forces inside. Okay, first things first, let's find the total mass of our sled train. We just add them up. 12 kilograms plus 11 plus 7, that gives us a grand total of 30 kilograms. Easy enough. Now we bring in Newton's other famous law, his second law. Force equals mass times acceleration, or F equals ma. We know the force, 120 newtons, and we know the total mass. So, a quick little calculation. We take our 120 newtons of force and divide by the 30 kilograms of mass, and that gives us an acceleration for the entire system of 4.0 meters per second squared. And that's key. Every single part of this train is accelerating at that same rate. Okay, now for the really cool part. Let's zoom in and isolate just the very last sled. We know its mass is 7 kilograms, and we know it's accelerating at our system rate of 4 meters per second squared. So ask yourself, what's the only horizontal force making it move? It's the tension from rope A pulling it along. So we just use F equals ma again, but only for this one sled. We've got 7 kilograms times our acceleration of 4 meters per second squared, and that gives us a tension in rope A of 28 newtons. That's it. That's the force it takes to pull just that final sled. All right, so what about rope B? Well, rope B has a tougher job, doesn't it? It has to pull not just the last sled, but the middle one too. So this time, we isolate those two sleds together as a single group. Their combined mass is 11 plus 7, so that's 18 kilograms. And of course, this little group is also accelerating at that same 4 meters per second squared. So let's run the numbers one last time. We take our new combined mass, 18 kilograms, and multiply it by our acceleration of 4 meters per second squared. And that gives us a tension in rope B of 72 newtons. And that makes perfect sense, right? Rope B has to pull more mass, so it's under way more tension than rope A. So you might be thinking, okay, sleds and ropes, cool, but why does this really matter? Well, because these aren't just abstract textbook problems. This stuff right here, this is the language engineers use to literally build the world around us. Understanding these internal forces is absolutely fundamental. I mean, think about it. Whether you're an engineer designing an advanced prosthetic limb that needs to move just like a real one, or you're designing a massive suspension bridge where steel cables have to hold up thousands of tons against gravity, the exact same fundamental principles of tension we just walked through are at the very heart of it all. So there you have it. We've unraveled that tricky puzzle or static tension, and we've broken down the chain reaction of forces inside a moving system. You now have the basic tools to look at the world and see how forces are transmitted through all kinds of connected objects. So, my question to you is, now that you have these tools, what complex system are you going to break down first? Thanks for joining me on this one.